I'm here in the garage with the KX45ED1, also known as the Japanese PVM-4300. It is the largest commercial or professional CRT that was ever made and sold. And this is quite possibly the last surviving unit in existence. At least it's the last known one. None of the others are documented. I've been working on this thing for the past week. We've had the back of it open here and troubleshooting it, trying to fix some convergence issues. It's working, but there's a few things we need to find and fix. So I'm really trying to tune it in and get it just right. So I thought I would take a break and kind of do a technical overview of because there's not much documentation out there, what this monitor is, what it can do, and how it works and what it looks like on the inside. So first, let's start with the monitor itself. So it has a 45-inch tube and a 43-inch viewable, and it's a Trinitron tube. So this one, unfortunately, does have what's known as cataracts. So you can see here it's having some, there was a safety glass on the front of this. So it's the tube. There was a layer of safety glass that was like glued on with some sort of like jelly adhesive, and over time that it has like decayed. So you can see here and here there are some, and here at the bottom there's some where while it's on and running, you can hardly see it, but it is something that has happened. It's mostly visible when it is off and you have a glare running to it like that. So that's the bummer. It is fixable, but it's a really risky procedure. So I'm not sure if I'm ever going to take that on unless it really gets bad. So I would say there's three versions. Well, there was three versions of this monitor. There was the PVM-4300, there was the KX45ED1, and the KX45ED1T. So the ED1, the difference between the 4300 and the ED1 is that this was the Japanese one. And instead of, we're going to go over to the primary difference first. So the primary difference is on this board here. This is the ED1. So on the primary difference is on the PVM-4300, instead of utilizing a JP21 connector here, it has two. Let's go back. There's two inputs for the RGB. So both versions have the S-video and composite and audio. This input here is the same, and it has this input. So everything's the same except this. So there are two inputs on this monitor. There's a 15 kilohertz and a 31 kilohertz input. This monitor runs at 480p. It is always running at 480p, but it has 480i or 15 kilohertz inputs. So how does it do that? So first, the way the monitor works standard is it actually has a full frame buffer, and I'll kind of talk a bit about that. So it has full frame buffer deinterlacing on this to take the 15 kilohertz or 480i image, deinterlace it, and display it as 480i. Now, that's cool that was really impressive at the time. Like, it was some expensive hardware, but our modern deinterlacers are obviously much better. So a 31 kilohertz input, a 480p input, just bypassing that circuitry would be awesome. And most Sony HD CRTs really suffer from not being able to bypass that circuitry. But this monitor was very forward-thinking in that this BNC input, this RGB-HV, bypasses. It allows you to bypass. So there's two inputs. One runs to the 15 kilohertz input, where this runs up here. This runs into the circuitry where it's deinterlaced and converted to 480p. And this mode here, the 31, that's this BNC input here. These bypass that and run a 480p signal straight into the monitor. And I can run 960i or any 31 kilohertz, 60 hertz video signal into this. And it works really well and it looks awesome. So this is like the redeeming quality about this monitor. So the 4300 has this as well. It has these BNC for the 31 kilohertz. So 31 kilohertz is 480p, and 15 is 240p and 480i. So they have the same input for the 31 kilohertz input, the 480p input, but on the 4300, the American version, instead of it using a JP21, which is a SCART but a different pinout, it uses a second set of BNC inputs. So that's the primary difference, and it also has a switch so you can run sync on green through this. But you can use external stuff to run the sync elsewhere. It doesn't affect video signal quality, doesn't introduce issues. They're really cheap. So the difference is really minimal. The only significant difference is just which connector it uses for the RGB, for the 15 kilohertz, which honestly no one would ever use in a modern day. They'd all just run it into this with external scalers because they're just so much better than the internal scalers. As impressive as the scalers were back then. So there was actually two versions. So let's go back to the front. There was actually three versions of this monitor. I've talked about the KX45ED1, the Japanese version, and the PVM-4300, which was the American version. But there's actually two versions of the Japanese version. There is the KX45ED1 and the KX45ED1T. So one without a T and one with a T. So what the T stood for was that it was more of a TV because it had a tuner built in. So on this bottom part here, you can see this whole unit below this. There's this shelf here, and then you can see this is the tuner here at the bottom. So I've removed these screws here, so you can see the tuner was not internal to the TV. So this is a monitor that was like sort of converted to be a tuner, converted to be a TV. And the tuner is like a pseudo rack mount thing that's on these pull-out sliders, like a drawer. And it's just used as a standard off-the-shelf Sony tuner. So when I got this one from Japan, this part here, this door was broken, and this. So I was able to find the same door here. I was able to find the same faceplate from another one. I just bought this off of Yahoo Japan, paid like $5 for the unit, and then like $80 for shipping, because they're so heavy. And I was able to swap the faceplate. So here's the old broken faceplate there. And now this one has a working unit. So this was just a Japanese TV tuner to run that. And the other thing it came with was speakers, which clip onto the side. I don't have it here because I have it open. And I'll show that. You'll probably see that in my other video or other photos and stuff I take. But another thing, so the T model came with the tuner and the ears. And another thing, this is the original stand for it. Unfortunately, one of the doors was damaged due to time, and it was shattered, and probably the pieces were lost. But this is the original. This is an original door with the original stand, and the stand weighs probably about 200 pounds. I've got it on these wheels right here, so it can be wheeled around and stuff. Let's go over a few of the accessories. This one here is the remote. So the remote's pretty crazy. So it has this flip-up door here. So flip up, and this has multiple pages. So the VTR, I don't know what MDP is, and then another blank one, so you can write your own. And it has the ability to take a remote, take a TV remote and point it at this and program it, which for 1989 was pretty impressive. Also have some documentation here they sent with it, which is a really cute quick start guide. It's a little eroded. And another funny thing that the original owners gave me was this little earthquake kit. So this came with the monitor. There's a few cables and the like, but there are these mounts to mount it to a wall to make sure in the event of an earthquake it doesn't just topple over and your $40,000 TV just destroys itself and or the floor. So I'm going to put this back here. So let's see. So What's next? Let's stop for now, and then I'm going to switch to the back and do a bit of a technical overview. Alright, before we peek at the back, there's one more thing I want to show off. So here is this is the tray where all the controls are. So this is actually a, normally this tray covers here. Normally there's a tray right here that covers it here. But for now, we'll get to those pots later. But for now, let's look at these controls. So this tray, which clicks and pops out, this lets you adjust the volume. That's, volume for the speakers. Picture, which is like the equivalent of contrast, lets you set the inputs of video 1, 2, and 3, as well as RGB. And RGB, which one it selects is depending on the switch we went to on the back of it. We showed off on the back of it. Whereas on the 4300, the American model, it appears that the switch, instead of being there on the back, is right up here, according to the documentation I've seen. This is a reset button. This adjusts the hue, like how green or red it is, color, brightness. Like the hue and color are really only relevant for like NTSC video inputs, not as opposed to the RGB inputs. Brightness, that controls, the brightness, like the black level. Sharpness, you've got treble and bass for audio, as well as balance. So here, the still button is interesting. So the still button, because the whole thing, it has a frame buffer in it. When you press the still button, it freezes what's on frame. So you have a frame buffer, might as well use it. So the still button does not work for the 480p bypass. For the 480p input, this only works for the 480i inputs, or 15 kilohertz inputs, that are running through the frame buffer, that's really cool. So the fact that it doesn't work for 480p shows that it's not running through the frame buffer at all. It's completely bypassing it, which is awesome. So these are just some controls for in addition to the vintage Japanese dust here, we have controls for wireless. That's for like using a wireless remote on it. The wired remote, I believe there's an input on the back, and then manual, which I think is these. And then this is, I haven't messed with this color thing. I'm assuming this is like 65K versus 95K, but I haven't messed with that. And then here is the V-hold, which is used to, same as other CRTs, make sure the vertical hold lines up. So there's that, and now let's have a look at the inside. All right, so here we have the back. This is the back's taken off because I was just working on it. This is the U board. This is the first board where all the inputs and outputs go. This, from my understanding, this appears to be the only board that is, aside from that other one I showed there, that is different on the that is different between the Japanese one and the American one because of the input there. I haven't popped this out and peeked at the schematic to see how different it is, but you have this, as I mentioned before, the sync on green, the lack of the switch, and then the second B and C inputs for the 15 kilohertz rather than a JP21. So you have this. This is like your input board. So let's start with power. So power runs in here, and then it runs to these boards here. So these aren't like the power supplies. These are like kind of like filtering stuff. So these are, I'm going to explain my understanding of it, which may be not entirely accurate, but runs through some inductive chokes there, kind of cleans it up a bit. And then I was told that these resistors, so it has these giant resistors here, that it passes through to fill up those capacitors. So if you're running straight from the power into those capacitors, then it would just pull way too much, blow, pop a fuse, blow a breaker, whatever. So what it does is it runs it through those resistors, and once it's fully, once the capacitors are full, then the relay right there flips and bypasses the resistors. So then it's, yeah. And then these are other things like for DGOS, you can see there's a PTC right there to handle that, to handle the DGOSing, which is all connected. And then, so now let's go from here. So that goes over to these power supplies. I haven't opened them up yet. They've been behaving pretty well, but I may want to peek inside and see if there's any touch-ups, because at certain brightnesses, it will, you'll hear some semi-quiet coil whine, which, but it's only like certain overall brightness, not like brightness or contrast, but like overall light output from the CRT, where if it goes below it or above that level, it doesn't make that sound. So I'm going to have to look into that. I suspect it's just, could be aging capacitors, or it may be something that's just can't be helped at all on that. So from the power supply, we're going to start with the deflection circuitry. So over here, there's actually like 4.5 deflection boards. It describes it as 5 deflection boards. So we're going to peek over on this side. So there's 2 here, and they flip out. So this one, I'm going to go through just kind of in order in my understanding. So it has 2 flybacks here. So this is where like the flybacks are here, as well as, and this is what's described here as a DC transformer. It's like a big DC block, and then here's a adjustment knob right there for focus. It's, to my understanding, I've been told it has, by the guys who are helping me out, that it has 3-point focus rather than 2-point focus, which is like, for reference, consumer CRTs will usually have 1-point focus, and then like the higher end and bigger ones will have 2-point focus. Like the FW900 has 2-point focus, and this allegedly has 3-point, which, I mean, given that the tube is just gigantic. Oh, here's another fun fact. If you look there, so it was made in 1989. You'll notice that the serial number here is 104, but everywhere else it says 103, which is kind of interesting. Like on the back and on the sides, which I have torn off right now, but yeah. So this right here is, this is deflection board 3 right here, and this was where our problem was we had earlier. And I'll get into that later, but this has like the dynamic convergence amplifier, as well as some of the other components that handle convergence and stuff. So let's go back over here. So the reason why I say it's like, so each of these boards, let me move my scope out of the way. Each of these boards will flip out, and you can actually examine each of them. So there's one here. This is deflection board 1. You can see there's a bit going on there with a heatsink. And here's the back. And now let's move up to this board. This one is, I believe this is another one of the deflection boards. Yeah, this is, here we go. There's that. This is CRT Protect. I don't see where it says. This probably says it here on the back, which board it is. Maybe D2. Yeah, D2. There it is. That's deflection board 2. And then I already showed you deflection board 3. So it considers deflection board 5 being these little transistors here. So these transistors, funny enough, let's go back over to deflection board 3. You'll see those, they run on wires to right, where was it? Here, to these connectors. So you can see this was labeled as if it were a transistor there, and it's got a big heatsink. So this may have been used on the other ED1 or similar CRTs, because this is the dynamic convergence power amplifiers. And these were, on these heatsinks, you can tell there are spots for heatsinks right there and there. So this was probably another board, and it was either in their design they realized it used too much power, or simply because it was intended for a smaller board and scaled up. So that's quite interesting. So up here, so let's go back. We've already looked at D2. Let's peek at it again. Yeah, D2s, that's where a lot of the power stuff's going on. You got the big transistors there. I haven't messed with D2 much. It hasn't been giving us too many issues, but we may be adjusting some stuff on it soon. And then this is P1. So this folds out. Here we are. Here's a look at P1. I'm presuming this is also pertaining to deflection somewhat. Or I'm going to look at the service menu as soon as this is over and find out that I was completely wrong. But all of this, so you can see how it's sorted out here, where all the power stuff is here on the bottom. You can see. So here's the power stuff. Over on the right, you have all of the deflection boards there stacked. And then over here is the RGB boards. And I haven't looked too much into these yet. Fortunately, I haven't had to have any issues with them. So here's this board. Let me scoot on over here. So this board here, you can see it pops out. This one's, I believe this is like the main RGB board. Where it handles it, you can see some EMI shielding there. The M board as it's labeled. So all of these are pertaining to audio, video, and stuff like that. And then this is B2 board. So you can see even more stuff's going on here. So I don't know what this one's specific. I could check the block diagram. Hopefully I'll have the service manual uploaded for anyone to be able to access it and find information on it. This one here I think is the most interesting board. It's covered in EMI shielding here. But this is what I call the money board, because this one is probably a huge portion of the cost of materials. So it's got this EMI shield here. And what it is this is where all the memory was. I'm going to pop this off here. You can see it's got all of these custom chips here. You know, going surface mount in the late 80s. But this thing's like a whole graphics card here, where it handles the video buffering. So it takes the whole video signal and it buffers it in like something crazy. Like from my measurements, it was like 16 milliseconds. So like one frame, which for gaming, you know, isn't like super ideal, but that's like, it does full, you know, active deinterlacing in 1989. It was full frame buffered deinterlacing, and it did it all in 16 milliseconds, which is faster than like even the Sony HD CRTs that came out like 15, 20 years later, which is really crazy. So here's the neck. We've adjusted some of the rings on the back, you can see. I need to glue those in their newly adjusted formats. And then here's the sticker for all of those curious. The CRT has definitely had some hours on it. It's been used quite a bit. And you can see it's got a big ol', here's hand for scale, big ol' anode cap. Then here's the neck board. It's kind of hard to access it, but it's really hard to like just capture just the sheer like size of this thing compared to my hand. The whole outside of it is like a steel frame here. So it just built like a tank with this back panel, like I showed before. And so interestingly enough, the back is metal, the front here is plastic, but this, you can see here, is actually, this like mid-frame here, is particle board, funny enough. So it's particle board that wraps around and goes up to over there. And let me talk a bit about what was going on here. So I'm gonna go back around and show the last board, and then so the last board here. So this board here is hiding here. This is the like fine adjustment of, lets you adjust so many things. So you have HStat, YBO, VAmp, HAmp. So these are all like mostly kind of like convergence controls. And over here you have landing. And these switches are cool because when you flip the switch. So it's standard. How do I describe it? It's like whenever you flip this, it doesn't show the regular picture, so it'll only show a red screen. And when you show this one, it'll only show green screen, and this one, it'll only show blue. You can like flip all three up to have it be white. It's really cool. And then you have, so like this lets you adjust landing, because depending on because when you get to larger tubes, the magnetic field of the Earth will start to affect it. So depending on which direction it's facing, you may need to adjust these landing. And these are all of these. Most of these were not working, and the convergence was really bad. So the red, green, and blue lines, instead of being lined up like this, they were like just very spread out. So and we were turning the static convergence all the way up, and it wasn't helping. And a bunch of these knobs weren't doing anything. A lot of these dynamic convergence controls, because it has so much, for its time, it has so much dynamic convergence controls, which, I mean, on a tube this big, you kind of need it. So here's what was going on. None of those knobs were working. So we went around and we looked at it, and we found what was going on. I can explain. So over here, we have, let me see where on the circuit is it. Over here, a lot of this, you can see those two transistors that are glued together, and you can see ones that were charred and stuff like that. So, and ones we've got heat sinks to replace. So one of the transistors for the dynamic convergence circuitry died. It just, it had died before I got it, and it created a cascading effect which destroyed many other of the components in there. And that was bad. Obviously, that's not good. So we went and we were going one by one, testing and replacing stuff, and the power amps were out of spec. So the power amplifiers for the dynamic convergence. We knew it was the dynamic convergence when we disconnected the dynamic convergence connector. That one, or it was one of these connectors that ran to the yoke, and we disconnected that, and then the picture got way better. So we knew it was the dynamic convergence, which, let me explain. Dynamic convergence is the 3 points. It's the red, green, and blue alignment at different spots on the screen. So you have static convergence, which adjusts the whole screen, but dynamic convergence lets you adjust convergence in different segments. So for example, with static convergence, fixing the left side may make the right side worse. So you need to adjust it on a zone-by-zone basis. And the dynamic convergence went out. We confirmed it was this, and we replaced the power transistors because they were out of spec, and it actually got worse. So replacing broken parts and then we replaced some other parts, and then things got really bad, like parts burned out. So you can see we had charring. You can see some like charring from that resistor went out, and a few other resistors went out. And those resistors saved the coil, because what was happening was there was another transistor we didn't find until later that was driving so it was like transistor into the power transistor, and one of those transistors was driving DC, which was pushing it harder. And by replacing those components with more capable things, they was more accurately able to send that bad just DC bias signal, which as a result broke other stuff. But fortunately, the resistors and stuff took the fall for us, and we were able to use that info to track it down further, and we were able to fix it. So now the dynamic convergence circuitry, if you happen to come across a PVM-4300 and your convergence is totally whack, try disconnecting the dynamic convergence. Disconnect the dynamic convergence coil. It's one of these on here. I think it might be C38, but don't hold me to that. I don't remember which one it was. But disconnect that, and if the convergence gets better, it's a problem with your dynamic convergence, check all the transistors and all of the complementary components around it. But once we did that, yeah, the dynamic convergence circuit on this is so cool. Let me talk a bit about it, how it works. So it sends a waveform where it is on the screen to it sends it into the input of all of these potentiometers. So it runs to all of these potentiometers, and because it does it all analog, it's really so fascinating. So the input from the CRT, where it is on screen and all that stuff, it sends a waveform, and that waveform runs to all the potentiometers. Most of the potentiometers here, the ones that control the dynamic convergence. Then all of those potentiometers run into these muxes. And what muxes are is they're like little switches. So it'll switch they can switch between multiple sources. So if you have 4 different things, 4 different inputs, you can switch between those 4 different inputs. So, but it doesn't use it like a mux, where it muxes it on one side and demuxes it on the other side. It's even crazier, because what it does is each of those inputs, each of these pots, so it runs into the pot, and then it runs each pot runs into an input of several muxes. And depending on where, so it will track with the beam. As the beam scans across the screen, depending on where on the screen it is, it will switch to different pots. And the pots will change the value that it sends out of the mux, and then the output of the muxes runs to the amplifier. So as the beam is scanning across the screen, depending on where on the screen the beam is, it is switching in real time. So remember, the beam scans from left to right at 31,000 times per second. And in different segments of the screen, so multiple times per scan. So you're looking at a multiplicative, this is switching at a multiplication of 31,000, depending on how many zones there are, and I don't recall. So maybe 60 or 100 or even more 1,000 times per second, this mux is switching between the pots, and depending on what the pot value is, each pot is assigned to a certain area in the screen. So it's doing this all analog, and then it just takes that whichever pot it's set to, it's just switching between them in real time. It's such a crazy way to do it, but I mean, it's the late 80s and it's analog, so it works really well. But last night we were able to fix that dynamic convergence circuitry. It's the whole thing isn't really it's not fully calibrated. It's still got a ways to go, but I'm really excited that we got it working, and the picture looks great. You'd expect on a TV this big at 43-inch viewable that it would have lots of issues, but there's so much that the circuitry is so sophisticated that it gives a lot of control to be able to compensate for the larger size. So it's honestly, this thing is, I've worked on a lot of CRTs before, but this one is relatively, even though it's super sophisticated, the fact that there's so much room in the inside and everything's so neatly laid out and organized, and all the cables just have labels on them. Yeah, the cables are labeled, and all the boards are just easily you just fold out and you can probe them and stuff while it's running. It's just an awesome set. You'd expect something that's gigantic to just be a pain in the butt to work on, but this was clearly a lot of passion was put into designing this and making it really easy to work on and well thought out. So I am super excited. Just thought I would do what I can to document as much of the inside of this board as I can. So thank you for watching.